When we were discussing the idea of correlation, we introduced the idea of sort of a trend line that would fit our scatter plot of our paired data points. And the least squares regression line is the name of that line. So this whole video is going to be focusing on how do we find the line that best fits that scatter plot. After we're done talking about that line, we'll focus on why we care about it and how useful it is. And this is actually in my opinion, one of the coolest and most interesting topics of the semester, but I'll save that for when we get there. So for now, I want to talk about the idea of, so this being the line of best fit. So this is the line that best fits a set of ordered pairs. Okay, so we did the example before where we talked about basketball points per game and salary. This would work on any one of those scatter plots that we talked about before, and then we can come back to the applications again in just a little bit. Okay, so let me do a quick example and show you a couple of pictures. So I'm going to try to draw in these two graphs two identical sets of data. So here's a point, a point. So here is a random set of data. I'm going to see if I can copy something that looks roughly the same over here. Okay, so these two pictures are meant to be identical, the same set of data points. And I want to draw two lines and think about which one of them best fits the data. So here is my first line. It's going to go like that. And here is my second line. Okay, so here are my two lines. Which one is a better fit, I should say. So which line is the better fit? Well, hopefully it's totally obvious to everybody watching this that the first one is a much better fit. So this is much better, and the one over here is much, much worse. But how do we actually determine this? What are the visual cues that we're relying on when we make this determination? I look at this one and I see that it's the better fit. I look at this one and I see that it's a worse fit. But how? How so? How do we know this? So what are some of the things that we think about? The responses I get for a question like that a lot of time is that this line kind of follows the data and this one doesn't. And what it really boils down to is the idea of distance. Which one of these lines is closer to the data on average? So I'm going to draw in some distances here as little vertical lines. And all these ones are pretty close. So these little vertical lines, we're just going to measure the distance in the vertical direction. So sort of along our y-axis, let me label these y and x. Y and x. And you can see all these distances that I just drew in here, they're all pretty tiny. Whereas over here, if I draw in those same distances, just the vertical distance between the line and each point, they're much bigger distances. And this is ultimately what we're going to use. So I want the average distance between the line and the points to be as small as possible. Whenever these distances are small, I know I'm winding up with a line that's a better fit. So which line is the better fit? It's the first one. How do we know? So the first one. How do we know? The average distance between the point and the line is smaller. That's how we know. All these little distances, on average, they're smaller here than they are over here. So that's going to be the way that we're going to basically determine what the best fit line is. We want it to minimize the average distance. But notice one thing happens. So I'm going to take a look at this now, and let's think about what would happen if we actually took the average of these distances. So if we define the distance be given by the following: y minus, we'll do a y with a little hat over it to use these as different symbols, where y, this is going to be the equation of, let's say, the points, because we've already used that. So it's the height or the y values of the actual points. And this y hat, this is going to be the height of the line. And so we're taking the difference between these, and that difference is these little distances that we're going to find. So basically, if I think of this point right here, if I look at those 2 points, one is the point on the line, and one is the point itself, and I want to find the difference between them. So on the line, this is our y hat value, and the point itself is y. And the difference between them, if I do y minus y hat, I'll get that little distance right there. So that little tiny distance on all of these, same thing over here, this distance is what I'm talking about when we talk about y minus y hat. So again, y is the equation of the point, y hat is the equation, or is the y value, the height of the line. So I just want that height minus that height, and I'll get a difference that gives me that distance. So this is the idea that we're looking for in all of these. Okay, so the distances are given by this expression, and we want the smallest possible values on average, at least. Then what we should do is basically try to take the average. So we'll take the average one of these distances. Oops. This is an average. Again, we're adding a bunch of stuff up and then dividing by how many things we added up. We've seen that that in general is always an average. What is it an average of? It's an average of what's showing up here in the parentheses, which we just said are going to be those distances. So basically what I'm suggesting is we need to add up all the distances and then divide by n. And if we look at these pictures, let's think about what would happen as we add up all of these distances. Well, keep in mind that the way we're defining it is the height of the point minus the height of the line. So for example, this first one over here on the left graph, the height of the point minus the height of the line. The height of the point is a little bit higher than the height of the line. So when I do that subtraction, the point minus the line, I'll get a little tiny positive value. And same thing here, a little tiny positive value, same thing here, a little tiny positive value. When we look at these other 2 points that occur below the line, again, we're doing the point minus the line. So I'm doing a smaller value minus a larger value. When you take a small number and subtract a large number, so if I did, let me just do it off over here on the side. If I did 1 and I subtract off 2, we wind up with a negative number. So all of these points below will contribute a little negative value. So these ones will have a positive distance, and these ones will have a negative distance. which doesn't really make sense. You can't have a negative distance, but then we're going to add them all up and divide by n. So I'm taking some positive numbers, 3 little tiny positive numbers. Looks like this negative is almost the exact same size as this positive. So if I added these two together, this little positive number and this little negative number, they'd pretty much cancel out. And these little two positive ones would add up with this slightly bigger negative one, and it looks like they would cancel out. These two small positives with a slightly larger negative, they'd cancel out. And so when we sum up all of these distances, of some positives, some negatives, we will wind up with 0, which is good. That's a small number. But what happens over here? Again, the point minus the height of the line is how we're computing our distance. So over here, again, any point that's above the line will give a positive distance. Anyone that's below the line will give a negative distance. And if you look at this distance is the largest. This one's a little bit smaller. This is a little bit bigger than that, and this is maybe the second largest. And this one's like right on the line. If you take the positive contributions from these two and add them to the negative contributions from these two, we're going to get something that looks like it's really close to cancellation again. We're going to add them up, and we're going to get really close to 0. We're going to get essentially the same result that we got over here. So this idea isn't working. We can't actually use this. What I'm suggesting is we added up all the points and we got something close to 0 over here. We added up all the distances, I should say, and we got something close to 0. We did the same thing over here, added up all the distances, the positive distances, the negative distances, and we wound up with something close to 0. It looks like we would get something close to 0, and it doesn't work. But clearly this is a better line than this one. So why are they giving me the same result? Well, it turns out the issue is basically that I don't care whether the distance is positive or negative. I don't care if the point is above the line or below the line. I just want it to be close to the line. So essentially what I'm suggesting is I want to add up all these distances without taking the signs into account. And how do we do that? How do we get rid of the negative signs so we don't get cancellation? Well, we did this exact same thing back when we talked about the variance and the standard deviation. We squared the values. And that's exactly what we would do here. So instead of taking the values and adding them up, what we would do is we would take, so instead, I'll just write it here in red, what we'd really want is we'd sum the y minus y hats, and we'd square them all and divide them by n. And this would be the thing that we want to minimize, because it makes it so we don't care about whether the point is above or below, and they don't give me the cancellation. If I square this distance, it'll be positive. If I square this distance, which starts off negative, it will also be positive. And as long as I minimize those distances, according to this formula, as long as I minimize this, we'll have the best possible line. So that is the idea. We want to minimize this. So minimize. Okay. Hopefully that makes some sense. That would give us a much bigger number in this case than in this case, and we would have a measure that says, yes, this is a much better line than this one, because this number we'd get out of this formula here would be much larger in this case when we square all these numbers and add them up than over here if we square all these numbers, all these distances, and add them up. Okay. So this is the idea behind how a least squares regression line is computed. This is kind of the theoretical stuff. However, this word minimize here is kind of an intimidating word. How do we minimize a formula like this? And it turns out the way that you minimize a formula like this is using calculus. And obviously I'm not going to derail us and teach you a bunch of pre-calculus stuff so that we can learn calculus to learn this one concept and actually derive a formula for this. We're not going to do a sidetrack and teach you guys calculus. So I'm going to ultimately just give you the formula, but the idea behind the formula that I'm going to give you, the place that that formula comes from, is from trying to minimize something that looks like this. That is the idea behind it. And that is why it's called the least squares regression line. Least, meaning we want to minimize it, and squares because we had to take the squares of all of the numbers. So the least squares regression line is the name of this trend line. And it's called the least squares regression line because we are minimizing the squares of all of these distances between the points and the line. The word regression has to just do with this general idea overall of trying to fit a line to a bunch of points. We're doing a linear regression. Turns out there's other nonlinear regressions that you would use. In some of those cases I said that we'd ignore, where a scatter plot follows a path that isn't a line, something like that, and it'd be better fit with a curve instead. So there's such a thing as nonlinear regression. We're not going to worry about that though. So for us, it's just trying to fit the best possible line to a set of points here. And that's the idea of regression in general. Okay, so coming back to this, I'm not going to teach you calculus. But that's where this formula comes from. Okay, so let's look at that formula. I'll do it as a definition here. Okay, so this is going to be similar to the one that we'd use for the correlation coefficient, a lot of the same stuff. If we're given a bunch of ordered pairs, x comma y, so a list of x values, a list of y values, the same ordered pairs we were talking about before, with sample means, so this will be similar as well, with sample means x bar and y bar, sample standard deviations of sx and sy, sample size of n, which we don't necessarily need in this formula, but good to have it. And let's say we've already computed the correlation coefficient. R, then the equation for the least squares regression line is the following. And maybe I'll start abbreviating this as least squares regression line is, so it's the equation of a line, which means it's going to look kind of like y equals mx plus b, if you remember that. But ours is going to look slightly different. It's going to be b0 plus b1x. And instead of y, I'm going to put that little hat over it. Again, the hat is just to distinguish that this is the equation of the line. We already used the letter y by itself without the hat to represent the actual values of the points up here. So I need a different symbol because it's a different y value. The y that we used up here is the heights of the points. The y with this little hat over it is going to be the height of the line. So just keep that in mind. Okay, so here is the formula. You may be more used to something that looks like y equals mx plus b, but we've just changed the letters. Our book uses b0 and b1. This right here, the m, this is the slope, and over here, the b in this case, this is what we call the y-intercept. You may remember some of this from an algebra class. In our case, they have different names. Notice the slope, m, is always going to be the one that's attached to the x, that's multiplying the x. So for us, this is the slope. The b1 is the slope. And that means the other number, where we're doing a plus, and it doesn't have an x attached to it, that must be this piece here. This is the y-intercept. So we changed the name of the letters and we switched the orders that they show up in. We did b0 plus b1x instead of mx plus b. The term with the x came second instead of first. But for addition, addition is commutative. The order doesn't matter, right? 1 plus 2 is the same as 2 plus 1. I can switch the order of the term that's a constant and the term that's multiplying x, and it won't make any difference. So just keep that in mind. So here's the formula for it. But now I need to tell you how we actually come up with these numbers b0 and b1. So here's the formula, but it's where b1, the slope, is going to be equal to r times s sub y over s sub x. And this is the slope. And for the second one, I guess I should write it down here, and b0 is going to be equal to, in this case, y bar. So basically this y with the line over it is the average value of the y's. So this is the mean minus b1 x bar. Okay. So here's the formula. And again, this formula, deriving this formula, comes from calculus. It requires calculus. But this formula, finish this sentence, and this is the y-intercept. I also just want to point out before we move any further and you start to freak out, we're going to basically be doing all the stuff that we're doing here either on the graphing calculator or using like Microsoft Excel. So you don't need to worry about doing this type of stuff by hand, although it's kind of possible. That's not going to be the focus. I don't want you to spend all your time trying to evaluate formulas by hand. We're going to do this using technology. Same with the value of r. In the previous video, we didn't actually do any examples where we found r. I'm going to make a separate video where we do an example and I show you how to do that example on the calculator. So keep that in mind, on the calculator and in Excel, I should say. Okay, so here is the formula. And let me just give you a quick little bit of intuition for, again, why are these the values that we're using. So let's start with the b1. Why is this what we use for the slope? Well, we talked a little bit before about the idea that in a situation like the one that we've got over here, where our data is increasing like this, we said we would expect to see a positive correlation coefficient, right? R should be a positive number corresponding to the positive slope of the sort of trend line right here. That is actually the role that R is going to play here. Remember, R is bounded. It's stuck between -1 and 1. But its sign will dictate whether our line is going to go up or down. So our correlation coefficient will determine whether we get a positive slope or a negative slope. But it can't capture really steep slopes. So let's just recall real quickly that R is stuck between these two values, -1 and 1. But it's totally possible. What if I had a set of data that looked like this? I drew that really crooked, so let me try to do this a little more carefully. So consider the following. Okay, so I want it to be a really steep set of data. This is my x, this is my y. Clearly the trend line is going to look something like that, ballpark. It's going to be really steep. But the slope of this line is greater than 1. So hopefully you'll remember from an algebra class, how do we determine slope in words? Slope is often thought of as, slope is often thought of as rise over run. You may recall that little phrase from an algebra class, rise over run. And what it's basically saying is I'm going to take how high up this thing goes, how high it goes in the vertical direction and compare that to how far it goes in the horizontal direction. So this is the rise, and this little distance down here would be the run. And I want to take the ratio of those. For every amount of distance you go in the x direction, how far do you go in the y direction? That is our slope. So if we look at this, there's a lot more rise than there is run, meaning this number on top will be much bigger than the number on the bottom. We would get a number bigger than 1 here. In this case, it looks like ballpark. I would say that maybe the rise looks like it's 3 or 4 times bigger than this. Let's just say 4 to make it easy. In this case, our slope is maybe approximately 4, just ballparking it. So I can't just use r by itself because r tops out at a height of, or at a value of 1. We wouldn't be able to get these slopes that are greater. But that's what the second part does. This sy over sx is going to be what gives us a 4. So think about what these sx and sy represent. Remember, sx, yeah, I'll just keep writing in red. Sx and xy, sx and sy are the standard deviations in the x and y direction. And what does standard deviation measure? What is it a measure of? It is a measure of how spread out the data is. So if I look at this, the spread of data in the y direction is pretty big. Sy is large. And what about the spread of data in the x direction? Well, I'm just going from this point, that's the furthest left, this point's the furthest right. It's not very big. We have a little tiny sx that's small. And the ratio of the amount of spread in the horizontal direction compared to how spread out these dots are in the vertical direction looks like a ratio of roughly maybe 4 to 1. And that's exactly what we wind up with over here. We're comparing how spread out it is vertically to how spread out it is horizontally. So the r is what gives us the correct sign, whether the slope is going to be positive or negative. And the sy over sx, the ratio of the two spreads, is what gives us the actual steepness. How much larger is stuff spread out in the y direction compared to the x, or maybe how much less spread out is it in the y direction compared to x if it's a really shallow, sort of flat trend line, which is also a possibility. So that's an explanation for why this formula works. Why is this the formula for B0, for the y-intercept? Essentially, the idea here is that it goes back to the idea of when we drew our picture. You may remember in the previous video, we drew a picture that looked like this. I'm going to erase it in just a minute, but we had some dots, and I drew these lines. Let me put the dots a little more clearly. It's something that looked vaguely like this. And I put these lines and separated it into quadrants, and they occurred at x bar and y bar. And so this point right in the middle, let me do it in a different color. This point right here is the point x bar comma y bar. And it's right in the middle of our lines, of our dots, I should say. It's right in the middle. And it turns out our regression line needs to go straight through that point. It has to pass through that point because that point is by definition right in the center of our data set. So it makes sense that the line that best fits the data should go right through the middle of the data. So what we're doing here is we're taking that point, x bar and y bar, and we're taking the slope, b1 that we just found, and we're using that to trace back to the y-axis. So basically what we're doing is algebra. We're saying, I know what the slope is, I know I have to go through this point right here, and I know I have to go in this direction. Let's follow that to see, oh, sure enough, there is the point that I'm going to hit the y-axis. That should be the y-intercept for this particular line. you would do it the same thing here. This one just coincidentally looks like it goes through the origin. It doesn't have to. It can go through any height, positive or negative, on the y-axis here. But that's the idea. It's taking a point that we know is on the graph, which is x bar, y bar. We know that should be right on our least squares regression line because it's literally, by definition, the middle of our data set. And our line should go right through the middle if it's the best fit. And we're taking that point, we're taking the slope, and we're using it to kind of trace back and say, I know I go through this point. I know I need to, my slope tells me I go this direction. Let's just trace that back and see where that winds up hitting the y-axis, and that should be our y-intercept. So that is the idea of how the second piece works. So that is where B0 comes from. So I guess I can just leave that there. But that's the idea. So this is the formula. We will do an example. I could do one by hand where I give you the values of Sx and Sy and the correlation coefficient, and we could plug them in and come up with everything. But I'd rather just do all of that on a calculator. It's not a useful exercise to just plug a bunch of numbers in necessarily. I really want you to understand the idea behind it, and then I'll show you how to actually calculate this for a real data set in another video. We'll do that. Okay. So the part that I really want to talk about is the following. So we've done all of this. We've come up with these formulas. We didn't even bother to use these formulas. I promise we will use these formulas and, in fact, use something better than these formulas when we do these on the calculator and in Excel in an upcoming video. But for now, I want to think about still just big picture. Hopefully this is the question running through your mind. Why do we care? Why are we doing this? What is the point of all of this? So far we don't really have a good explanation, a good answer for why do we care about the correlation coefficient? Why do we care about this least squares regression line? Who cares? And it turns out there are plenty of reasons to care. The whole point of the least squares regression line, so the main idea is that the least squares regression line, which again I'll abbreviate least squares regression line, allows us to make predictions. And this is an incredibly important thing. So super underline this point. This is the whole reason we're doing any of this. It allows us to make predictions. What do I mean by that? If we go back to the example of the basketball players from the previous video, draw that a little more carefully here. And again, I'll just do hypothetical. We had points per game down here. This was our X variable. We had how much money they make. This is the Y variable. I recall that this went 10, 20, 30. These were in millions of dollars. Same thing down here. We had points per game. 10, 20, 30-ish. And we had some points. And I'm just going to make them up. I'm not going to copy them exactly. But we had something that looked like this. And we say, okay, that gives us the following line. Maybe this is what our line winds up looking like. So this is our least squares regression line. Imagine we found that line. How is this useful? Well, we can use this. If we were a basketball executive, if we were a coach or a talent evaluator, a manager, somebody that worked for one of these teams, we could use the data for how existing players are paid to try to determine what a fair market value is for somebody that we're trying to make an offer to or try to retain on our own team. So maybe we have a player that scores this many points per game right here. So maybe this is where our player is. They score right here. They score, 12 points a game or something like that. well, we have data for somebody down here that scores a little bit less than that. We have data for people that score more than that. We have data for people that score way more than that, or quite a bit less than that. And we have this line. I don't know what a fair value is to pay this guy because uh, they score more points than this person does. They score fewer points than this person does, right? And here's sort of the general trend line of how people in the league are paid. Well, all we need to do is track this up to right here. So if this is the X value, maybe it's equal to 12 points per game. This will give me a predicted Y value. And it'll say, okay, you need to go back and this person should make, boom, $10 million. We can use this to make predictions where data doesn't exist, right? We have a handful of points, but what if we want the information between points? That is the whole point of the least squares regression line. So it looks like someone who makes, or averages rather, I should say, averages 12 points per game should make $10 million a year, according to this data set, just ballparking it. How do we do that more formally? What we would need to do is actually take the formula that says, here's again, y bar equals b0 plus b1x. Once we know these values, if I want to figure out a y value, remember this is salary, so this is how much money they make, and we know points per game, we know this, all I need to do is plug it in. When we know the person makes 12 points per game, we plug it into the formula, and the formula will spit out a predicted value, in this case of $10 million. So I'm not going to guess at what B0 and B1 were here. We didn't find them yet. But I will do an example like this with real data using a calculator and or Excel coming up. But that's the whole point. It allows us to make predictions. And this may seem trivial and in this one little context, but it turns out the applications of this are incredibly far-ranging. This is the basis for all of artificial intelligence and machine learning. Oops. Regression is one of the most powerful tools that's used in that field. So, for example, if you've ever bought or sold a car and you've used Kelley Blue Book to come up with a fair price for that car, it uses this exact same kind of prediction tool. It uses regression. So, Kelley Blue Book to price a car. If you've ever tried to buy a house or rent, if you've used Zillow or apartments.com or something, one of those that gives you a fair price for a house or a fair price for an apartment. Netflix used to use this to make predictions about what types of shows you would like back when I'm old enough to remember when you had to rate individual shows uh, from like 1 to 5 stars, and it would make recommendations based on those ratings. Amazon, it uses information based on the products you've purchased that it assumes that you like to do regression to try to predict what things it think you may also be interested in purchasing or what other people put in their carts to try to basically come up with predictions for what you would be interested in using. Um, Honestly, this is used in self-driving cars. If you've ever had to use the CAPTCHA system where it shows like an image of something outside, something on a road, and it sort of blocks it up into a grid and says, click on all the squares that have a car in them, or click on all the squares that have a stop sign in them, or something like that. In that case, what you're essentially doing is giving a piece of data to teach. Notice it's always Google that does this. It's Google's self-driving cars. They're the ones working on the software. You're teaching the computer what a stop sign looks like. You're teaching um, the computer what another car on the road looks like by using your human eyes to basically train the computer. And then it makes decisions where it basically takes a picture while it's driving, and maybe, here's the picture you just did. You had to grid it up and said, oh, you clicked on, here's the road that you're driving on, and here's a stop sign over here or whatever. And there's another, a house over here and a tree over here and whatever. And you click on this one and say, oh, these all have the stop sign in it. Then when the car is actually driving, maybe it encounters something similar. Maybe the house is over here on this side, but maybe there is no tree and the road's shifted a little bit closer, but it spots something that looks like this and it says, oh, I think this is a stop sign. I've got to stop because this image is similar to this other image I saw. And over here, this was taken with the real driver. And at the moment that this picture was taken with the real driver, the person was hitting their brakes a certain amount, and they were starting to turn their driving, their steering wheel to the right. And so now that I see this picture that I think is similar to this one, I, the self-driving car, am going to hit my brakes and turn to the right. So it basically has a camera that takes in these real images in real time and interprets them based on input from human drivers to decide what decisions should be made and exactly in a novel situation. This road is a new road that the real driver never went on, but it's similar enough. They use the data from the real road to make decisions about what should be done in this case, to make predictions. So this is the power of the idea of regression. It's a really powerful tool. It's really cool. Long story short, regression and what we're doing, the least squares regression line, is a tool that's at the heart of machine learning and artificial intelligence. And there are engineers in Silicon Valley making $300,000 a year with a little bit more knowledge of the math and the coding behind it than what we're going into here, but this is the basic idea of what they do. So it's a really cool concept. For me, it's one of the most interesting things we'll talk about this semester. And in the next video, I'll show you how to actually use some technology, Excel, a calculator, to come up with these least square regression lines and use them to make some basic predictions.